everyone, my name is Bishakha and I'm going to present my final year project, which was versatile grasping for shelf placement of FMCG items. So versatile grasping is one of the most basic forms of robotic manipulation, and amidst the COVID-19 pandemic, the warehouse industry witnessed a huge need to increase automation. Considering the FMCG industry especially, there has been a surge in demand as the market was pegged at 10.2% in 2020, which was an increase from 3.4% in 2019. Therefore, the scope of this study covers the design and implementation of a shelf placing environment which includes FMCG products and contribute to the future of warehouse logistics. To achieve this, I was looking for a framework which could do many different kinds of manipulation tasks, and after conducting extensive background research decided to use Transporter Networks framework. It's actually from this paper titled Transporter Networks, Rearranging the Visual World for Robotic Manipulation, which was published at the Conference of Robotic Learning towards the end of 2020. These are the tasks which the paper experimented with, and as we can see, they are all tabletop actions such as block insertion or kitting. So for these tasks, the picking and placement are both happening in the same plane of axis. Therefore, all these tasks are limited to picking and placement with 3 degrees of freedom, which means that the gripper is free to change in X, Y, and Z positions. Conceptually, this is how the transporter network works. They find an area of interest which becomes the attention value, the argmax of which becomes the picking location. The picking location is used as the key and queried over the entire search space. So what they do is that once they find that area of interest, they overlay this region over several candidate placement configurations and then learn to choose the best one that is the most similar to what it had seen before from demonstrations. All the tasks for transporter networks were limited to picking and placement with 3 degrees of freedom. Therefore, it did not immediately satisfy our criteria because for shelf placement, the picking needs to happen in X axis and placement has to happen in Z axis. Therefore, the first contribution made during my final year project was to extend the transporter networks to work with 6 degrees of freedom such that the shelf placement could be possible. The next contribution was to design a shelf placement scenario and create a scripted Oracle agent providing expert demonstrations to enable the agent to train on imitation learning. Now I'm going to talk a bit about the simulation scene setup and will essentially go over each of these items one by one. Firstly, designing and implementing the shelf. These shelves have been implemented with URDF files and they have the properties of collision and friction to closely replicate real-world properties. Next, the dimensions for length and height are randomly sampled. The importance of randomly sampling the shelf sizes is that later, while creating the dataset, the objects will be created by dividing the volume of the shelf using a binary search tree. So if the shelf itself has random dimensions, it's easier for us later to ensure that the model will not overfit to the dataset because the dataset too will have random dimensions for every iteration that it runs for. So these are the FMCG items, or the fast-moving consumer good items, which were used for the task of shelf placing. Then we also used Yale CMU Berkeley or YCB Objects to facilitate benchmarking. They were used so that it is easier to reproduce the results from this work. There are 2 types of YCB objects being used, and the simplified mesh of the untextured and the textured objects have been shown. This was the design used for the camera placements. So we are using 2 cameras on the same X and Y coordinates, with one being perched higher than the other. Since the height maps generated uses combined point cloud information, we can also see that using 2 cameras gives us a better quality height maps for picking and placing. Now I'll introduce the Oracle agent. The first step would be to generate the dataset. As mentioned, binary trees were used to recursively partition the shelf. Once the shelf spaces are determined, rectangular blocks were created corresponding to the dimension of each split. These boxes then got individually spawned into the workspace in a collision-free configuration. For the shelf placing task using FMCG objects, similar space partitioning occurs, except FMCG items are spawned instead of regular rectangular blocks. So here are videos of the Oracle agent working. Once these objects are shelved, images are captured and saved so that they can be later passed down to the 6 degrees of freedom agent for learning. Then we come to the implementation of the 6 degrees of freedom agent. The 6DOF agent works by first attaining separate height maps and color maps for the 2 separate axes of actions, X and Z, and then it uses these height maps formed to calculate the rotation matrices, which is then used to find the Euler angles of pitch, roll, and Z. Those angles for the sample dataset would then be passed as labels to the 6 degrees of freedom trainer agent, which would then pass them through the attention, transport, and roll, pitch, and Z models. The transformation matrix M showed on the left side of the screen communicates the pose to the 6DOF agent after environment coordinates are converted to ideal camera coordinates, and another set of transformation needs to be applied to the homogeneous transformation matrix such that the 6DOF agent can work with the two different axes, and this has been shown by transformation P. This chart shows the rewards obtained for the agent trained to 12,500 iterations after 10 expert demonstrations. The model trained on FMCG objects over 10 demonstrations was tested with YCB untextured objects, and overall, the performance of the 6DOF agent seems to be similar on both the sets of untextured objects. Therefore, we can infer that the 6DOF agent trained on FMCG objects can be extended to use with YCB benchmarking objects, all of which were novel for the agent. The 6DOF agent was further trained on 1 and 100 expert demonstrations as well, in an attempt to compare the performance with the one trained with only 10 demonstrations. Generally, for each training iteration, it can be observed that the rewards for 100 demonstrations is above the one for 10 demonstrations, which in turn is above the one for one demonstration, which shows that the agent performs better when trained on a larger sample rather than a smaller sample. So this slide has some examples of successful placements happening. And as we can see, there were a lot of successful placements which occurred. So now I'm going to mention some of the modes of failure that we encountered during the testing phase. Firstly, we have false negatives when the object which got shelved was too small to be picked up by the camera. So even though it got shelved, it was not awarded any rewards. Then we have collision, which happened mostly with the hammers, and it's basically the hammer colliding as the agent tries to put it inside the shelf. And finally, we have post-placement faults, which means after the object was placed, it falls out of the shelf, and accordingly the rewards gets deducted. In conclusion, the implementation succeeded in designing and implementing a shelf placement environment which includes textured and non-textured FMCG products while ensuring agent movement with 6 degrees of freedom on two distinct axis planes. Thank you.